Good afternoon, everyone. So, welcome to my YouTube channel, Maths Avatarm. So, we were studying uniform quantity. Let's start its fourth lecture. Okay. So, you have seen several times in competitive exam the following types of questions. First question is, let fx is equal to 1 upon x plus 1. Define on close 0 to infinity interval. Then, which of the following statements is correct? Number one, f is not uniformly continuous. Second, f is continuous but not uniformly continuous. And third one is f is not continuous. And fourth one is f is uniformly continuous. So how to solve such question? Okay. Another question you see that let fx is equal to x upon sine 1 upon x upon 1 plus x square open interval 0 to infinity. Then f is uniformly continuous, f is not uniformly continuous, f is not continuous, and none of the above. So these are two questions. So how to solve this question in limited time? Because if we are sitting in a competitive exam, we have limited time. So how to solve such question in 5 or 10 seconds or maybe half minute? Okay. So for that we are going to study a theorem. See this theorem. Let a belongs to real number, okay, and f close a to infinity, be a continuous function. If limit x tends to infinity, fx exists, then f is uniformly continuous on close a to infinity, okay. So how to prove this theorem? So let's prove it first. Then we'll come to these two questions, okay. It is given that limit x tends to infinity, fx exists, okay. So this implies that limit x tends to infinity, fx is equal to L, and that is belongs to R, okay. So this implies limit exists, and I am saying that limit is L, okay. So now how we'll approach? Since limit x tends to infinity, fx is equal to L, so it means that given epsilon greater than 0, there exists b greater than 0 such that fx minus L is less than epsilon by 2 for all x such that x greater than b. Okay. Okay. Now my interval, close interval a to infinity, can be dissolved in two intervals, a close interval b and b open infinity. So my f is continuous on this interval. So my f is also continuous on this interval and continuous on this. Okay. Now f is continuous on close a b. This implies f is uniformly continuous on AB, because in last class we have studied result if a function is contains on a closed and bounded interval, then f is uniformly contains on that interval. Okay. So what does it mean? Now f is uniformly contains on AB. It means this implies there exists delta 1 greater than 0 such that fx minus fy is less than epsilon for all xy belongs to AB such that x minus y difference is less than y delta 1. Okay. So I am saying this equation number first, and now just we have got this one. I am saying is equation number 2. Okay. Later we will use these two equations. Okay. Now f is continuous on B. So we get by definition on country delta 2 greater than 0 such that fx minus fb less than epsilon by 2 for all x belongs to a infinity interval with x minus b less than delta 2. Okay. Now let's take equation number 3. So put delta is equal to minimum of delta 1 and delta 2. Since delta 1 and delta 2 is greater than 0, so delta is also greater than 0. And observe the following things. Let x and y I am taking from this interval such that x and y difference is less than delta. Then there are three possibilities. There are three possibilities. What are those possibilities? Case number first. Because xy belongs to my interval a to infinity. So, but interval a infinity is broken in two intervals, a b and b to infinity. So either both x and y belongs to closed interval a b. Okay. In that case, what will happen? In that case, what will happen? We have from equation 1. Equation 1, we have because xy belongs to AB interval and okay. So first possibility is that xy belongs to this interval. So in this possibility, what we will have, we will see it. So given that it is given that already xy minus is less than delta. So this is my case first. Okay. Given that xy is less than delta, but this is minimum of this is minimum of delta 1 and delta 2. So this is less than equal to delta 1. Okay. So this implies x and y difference is less than delta 1. So by equation 1, we have what we have from equation we have, because difference is less than delta 1. So what we have fx minus fy is less than epsilon. Okay. Now see case 2. Case 2 is xy belongs to this interval. Because there are three possibilities. Either xy belongs to closed interval AB, xy belongs to open B infinity, or third case will be x belongs to closed interval AB and B belongs to open interval B infinity. The second case is this. Okay. But in this case we have directly have this one. Okay. If xy belongs to this interval, from equation what we have? Equation 2, what we have? From equation 2 we have fx minus L is less than epsilon by 2 and fy minus L is also epsilon by 2. So then combining both the equation we have, then what we have? Then fx minus fy. You subtract L and add L. What you will get? This is epsilon by 2 and this is also epsilon by 2. What does it mean? It means fx minus fy less than epsilon. Okay. Now third case is what is that? This third is that x belongs to closed interval AB and y belongs to open interval B to infinity. Okay. Since x minus y is difference is less than delta. Delta is minimum of delta 1 and delta 2. And B is, because A belongs to this, B belongs to this, and it means B lies between x and y. Okay. Okay. So this means that x minus B is less than x minus B, that is less than delta, and because this is minimum, so it is less than delta 2 as well. Okay. And y minus B is also less than x minus y, less than delta, that is less than delta. Okay. So we have this one. So it means x minus B is less than delta 2. This implies fx minus fb less than epsilon by 2 by equation 3. Also, we also have y minus b less than delta 2. Again, by equation 3, fx minus, sorry, fy minus fb less than epsilon by 2. Now combining these two equations, what we will get? Then fx minus fy, you add fb and subtract fb. This is less than epsilon by 2. This is also epsilon by 2. Finally, what we get? Fx minus fy less than epsilon. So what we got finally from cases 1, 2 and 3, we conclude that given epsilon greater than 0, we have there exists delta greater than 0 such that fx minus fy less than epsilon for all xy belongs to a infinity with x minus y difference is less than that. It means f is uniformly continuous on A2. Okay. Now we have proven that if f is continuous on closed interval a to infinity and limit x tends to infinity exists, then function is uniformly continuous. Okay, we have proven. So now we see its one corollary. Okay. Corollary. So before corollary, you note one thing. Okay. Note one thing. Suppose let A belongs to R and f a to infinity is uniformly continuous. Then limit x tends to a plus fx exists. It always happens. You can see its proof. What is? Suppose my function f open interval a to infinity to r is uniformly continuous. Okay. Then I can choose b in between. Then f a b to r is also uniformly continuous. Because if a function is uniformly continuous on a bigger domain, obviously it is uniformly continuous on a smaller domain. So we already seen in last lecture that if a function is uniformly continuous on a closed and bounded interval, open interval, then right hand limit on A exists and left hand limit on B exists. So what does it mean? It means that limit x tends to a plus fx. Okay. So now we come to corollary. One corollary. Let a belongs to real number. Okay. And f a to infinity be a continuous function. Be a continuous function. If one limit x tends to a plus fx exists. Second, limit x tends to infinity fx exists. Then f is uniformly continuous on a to infinity. So its proof is really very simple. We will see it. Okay. How? Proof. I am defining a function f tilde. F tilde. How I am defining fx? I am taking, if I am taking x is equal to a, then I am defining limit x tends to a plus fx. If I am taking x in open interval a infinity, I am taking just fx. If, okay, so you see that then f tilde close interval a to infinity, close interval to r is a continuous function such that limit x tends to infinity fx tilde, that is nothing but limit x tends to infinity fx, and that exists. This limit exists. By previous theorem, by theorem of this lecture, we get f tilde is uniformly continuous on closed interval a to infinity. So this implies f will be also continuous. F is uniformly continuous on a smaller domain. On a smaller domain. But on a smaller domain, f tilde is nothing but f. Because if you take any f belongs to open interval, it is this, its value is given by fx. So this implies f is uniformly continuous on this. So hence the result is true. So we remark, suppose I am taking B belongs to, let B belongs to R. So I have let, then we can prove similarly if f minus infinity to B close continuous such that limit x tends to minus infinity fx exists, then f is uniformly continuous on, okay. Second, if f open interval minus infinity to B continuous such that 1 limit x tends to B negate B minus fx exists, Second, limit x tends to minus infinity fx exists. Then f is uniformly continuous on. Same proof can be repeated of the theorem to prove this remark 1 and 2. Okay. So this theorem is proved. Okay. So now we are going to solve the questions which we have seen in starting. Okay. So let's come to questions. Okay. So these two questions. So fx is equal to x 1 upon x plus 1. So my function is this solution. Let's see its solution. So fx is equal to 1 upon x plus 1 we have on closed interval 0 to infinity. So you see that in theorem I have told if a belongs to a is 0 and this is closed interval. If limit, now this function f is continuous on this interval. If this limit x tends to infinity exists, then function will be uniformly continuous. Let's see what is the limit. Is limit exists? So you see that 1 upon infinity plus 1, that is 0. So this implies limit exists. Limit exists. Hence, f is uniformly continuous on close 0 to infinity. So which option is correct? So option number 4 is correct. Okay. Now move to second example. Second example is on open interval. On open interval, the following function is fx is equal to x sin 1 upon x upon 1 plus x square. So if limit exists on both the boundary points, the function will be uniformly continuous. First we have to check whether this function is continuous on this interval. So this function is continuous. Okay, you can check it. The solution. Fx is equal to x sin 1 upon x upon 1 plus x square is continuous on open 0 to infinity. So what is the limit? X tends to 0 plus fx. What is that? X sin x. But sine function is always, sine 1 upon x is always less than equal to 1. So this is less than equal to limit x tends to 0 plus x upon 1 plus x square. That is 0. So this implies limit x tends to 0 plus fx is 0, limit exists. Now what about limit x tends to infinity fx? Same thing, limit x tends to infinity. X sin 1 upon x 1 plus x square. That is dominated by limit x tends to infinity x upon 1 plus x square. So I can still make less bit x tends to 1 upon x square. That is 1 upon x. That is limit 0. So this limit is also 0. So this exists, limit exists. Function is continuous on interval and both the limit exist. This implies f is uniformly continuous. Okay, so what option is correct? Option number 1 is correct. So both the functions are uniformly continuous. Okay, so we have seen today's lecture, how it works, today's theorem and corollary, all these things, how they work. So today's lecture up to this. Thank you very much. Please like, comment, share and subscribe my YouTube channel. Thank you very much. If you have any problem, please just write a comment on my YouTube channel. I will see that problem in next lecture. So thank you very much for today's session. Thank you very much. We will see you in next lecture. Thank you very much.